Alrighty, good afternoon. Welcome to today's webinar titled How to Know the Laser in Your AM System is Performing to Spec, presented by Ophir and MKS Instruments and hosted by 3D Metal Printing Magazine. My name is Brad Coogan. I'm the editorial director of 3D Metal Printing Magazine, and I'm pleased to serve as your moderator today. Before we get started, just a few notes about today's go-to meeting. The meeting is being recorded for archiving, and a copy of the recorded event will be posted to the website of 3D Metal Printing Magazine within the next few days. So be on the lookout for an email from us to let you know when that recording is available, so you can view it online and share it with others in your organization. Also, all participants in the meeting are in listen-only mode, which means that the speaker and other listeners will not be able to hear any audio from your site during the program. However, you can communicate with us throughout the program by submitting any questions or comments using that question box, which is located on the right-hand control panel of your go-to screen. So you'll simply type your question and label it to an organizer as selected from the drop-down menu. And then at the end of today's presentation, you'll use that same question panel to ask any questions you have of our speakers at the end of the presentation. And we should have a good 10 minutes or so at the end of the presentation to take your questions. So with all of that said, it is time to begin today's webinar, where you're going to learn the what, why, and how around the latest innovations in uncooled power meters designed for the AM workspace, as well as self-contained laser beam profilers that provide views of the working beam and monitor the location of the beam waste and any focal shift that may have been occurring. Our speakers today from Ophir and MKS are Kevin Kirkham. Kevin is the Senior Manager for New Business Development, and John McCauley, who is the company's Business Development Manager. Kevin has more than 30 years of experience in laser diagnostics and quality assessment, and John's focus is on automotive and directed energy applications. So John's going to kick things off and then hand it over to Kevin. John, go ahead and take the stage. It's all yours.
Okay. Thank you, Brad. Appreciate it. First of all, just would like to thank Brad and Marlene and Lou and everybody at 3D Metal Printing for setting up this venue to speak. It is always a pleasure to be given the forum like this to speak about these important topics that are very relevant to your job. And it is my hope that we can leave you with some information that is very valuable to you. They're doing great things at their publication, and we want to continue to support their efforts, and just want to thank you for the platform to speak here. So without further ado, let's get into our topic of the day: how to know if your additive manufacturing system is in spec. MKS Instruments has been a global leader in providing all kinds of laboratory equipment, but we are a market leader that is focused on strategic growth through innovative solutions. MKS founded in 1961. Ophir and Spiricon were founded in the mid 1970s, and so we are part of the motion photonics and optics group of MKS Instruments. Let's talk, just to kind of frame the conversation that we're having today, let's talk about the current state of additive manufacturing as a whole, just kind of a 30,000-foot view of what's going on. Additive manufacturing is definitely benefiting manufacturing and changing the way that parts are being manufactured and changing the way that people look at how parts are being manufactured. With additive manufacturing, you can have more customized manufacturing. You can use more materials, specialized materials that are being used in the parts that you're making, and it's also changed the way that distribution networks have changed. If you can envision, trucks, less trucks being on the highway because parts are being manufactured right there on site. Those types of things are being thought about with respect to how to make parts and how to utilize this very important technology. So it's definitely changing the minds of people and how they are taking a look at manufacturing. Industry 4.0, I think everybody is familiar with this particular term, but in general, what Industry 4.0 is doing is taking the technology that we have today, specifically the way uh, pieces of information is sent and the types of devices that are sending them are communicating with each other, taking that technology and really taking that and using it to improve the processes in which these additive manufacturing processes are involved in. So taking feedback from the additive manufacturing system, oftentimes real time, and adjusting the process in order to have a more smart way of making these parts within these systems. So the adaptation of smart machines shift from managing input parameters and variables to managing process variables is really kind of the mindset shift that's taking place. The reliance of in-situ system monitoring. So while a process is going on, what kind of feedback can be taken from the machine as the process is going on, and taking that information and using it to adjust the process to make it better, or at least have it remain consistent over the time of the build. Each part can meet specification standards. So each individual part that is manufactured can use this Industry 4.0 technology to meet a specific standard instead of just a batch run of parts. With respect to additive manufacturing, there are some challenges that we want to talk about specific to the webinar today. These first 4 bullet points, there are challenges with respect to protection of intellectual property. That is one of the challenges that continues to be discussed. It is still very labor intensive, so mass production costs are high. Because it is an emerging technology, and the emerging technology simply needs to go through those growing pains, but they are decreasing. These additive systems are becoming faster. They're becoming to the point where you can mass produce many parts where you could not do that before. So those types of improvements are being made. Understanding and managing large number of process variables is always going to be a challenge for any process, but with additive manufacturing processes, this still continues to be a challenge. How to measure those variables, how to manage those variables, and how to minimize change in those variables is always really going to be a challenge. Because a lot of these additive manufacturing systems utilize a high-powered laser, understanding and managing the variables that come with the laser itself is always going to be a challenge. And so that's really why we're here today, is to talk about these variations that can happen within a high-powered laser, how to minimize those variations, how to measure and analyze those variables, and then ultimately use those measurements to minimize any changes that may happen over the life of the laser, but at least over the life of the build from beginning to end of the part. All right, so today we're going to be talking about challenges that are unique to high-power lasers compared to other laser systems and processes. I'm going to try to make it as very easy for you as possible and ask the question, what single laser parameter is critical to material processing? There are all kinds of laser variables that you can manage, that you can analyze, and it can sometimes get very confusing on where to apply these. So I'm going to try to make it very simple for you and give you one single laser parameter to measure on your laser to ensure that you have a consistent process. This is comprised of 2 measurements. So what 2 measurements make up this parameter? How do we best understand this parameter? Why it's important to understand this parameter? And then what causes this parameter to change over time? And obviously ways to measure that change and to minimize that change. I'm going to talk about measurement technologies and techniques, because that's what Ophir does, is we provide the way to measure the laser performance and to help minimize those changes. I'm at this point going to pass it over to my colleague, Kevin Kirkham. He's going to talk about 3 case studies and where we helped customers over the years measure their laser, identify some problems, and try to help solve those problems. He's also going to talk about some general best practices in helping maintain your additive manufacturing systems. And then, as is customary, at the end of the webinar, we're going to open it up for a Q&A period at the end of the webcast. We suspect that the presentation will probably take roughly 40-45 minutes, and then we'll have 10, 15, 20 minutes or so at the end for a Q&A session. So prepare your questions, and we'll do our best to answer those questions you may generate. So high power laser processing challenges. First of all, I just want to make the statement that laser quality has really greatly increased over the years. When you compare today's laser technologies to back in the 60s and 70s, where lasers were first being used for manufacturing processes, the quality of the laser, the consistency of that quality of the laser has greatly increased over the years. There's, the cost of ownership has really decreased. The wall plug efficiency has greatly increased. There's decreased maintenance compared to older systems. So laser source manufacturers and laser system integrators, laser additive manufacturing OEMs have done a great job at addressing these problems that have arisen over the years, and really are doing a great job in providing high quality systems today. But that doesn't change the fact that lasers are still made up of physical matter, okay? Components of the laser systems, they will degrade over time because of the relatively dirty process environments that these lasers operate in. Components will still get dirty. It really is the silent killer, right? So you may, especially if you don't have a practice of measuring your laser on a consistent basis, it could be something that could really easily creep up on you and cause adverse effects to your laser process that you might not know about until sometimes it's too late. Laser systems, because they're made up of physical matter, these components do catastrophically fail from time to time. That's just part of having an electronic device, having a physical device. These things just happen because of the nature of the world we live in. So as a result, because of these degradation of laser components, as a result, sometimes, as an example, power decreases. So historically, what laser operators have done when their power has decreased, when the process starts to go to pot, typically what they do is just ramp up the power. So just turn up the power, keep going. But is this really a good way to, really address the problem that you have, and that is a degrading laser, or will it cause other issues over time? I think probably everybody knows the answer to that question. Changes in spot size can change how your laser interacts with your process. Your drift in focus spot location, so the location of the focus spot with respect to the process, if there are any changes or variabilities within those, that can affect your process. These two parameters will cause just a reduction in delivered power density, or fluence, as some people call it, to your laser. So what is power density? We'll talk about in a second. This is what we're all trying to avoid: losing time, increased scrap. We want to reduce the scrap that is produced, but ultimately time is money, and we want to reduce the lost time and the lost money due to scrap, due to variabilities in the laser, and that's kind of what we're here to talk about today. So is reducing these. High power laser measurements. So the one single parameter that I told you about at the beginning is power density, okay? So let's talk about power density and why it is important to understand this very critical characteristic of your laser. So power density is, as I define it, the measure of how the laser is applied to the material that is being processed, okay? You have laser light, you're focusing it down to a process, and where that laser light meets the process is defined by the power density, the efficiency of the laser, and how well that laser is going to produce the part that it's producing is defined by the power density. It's an expression that is expressed in watts per centimeter squared. You see that there. The top of the formula is watts, and this is defined by the amount of laser light that's being applied to the process. The bottom of the formula is represented by centimeter squared, and as you can conclude, that is a unit of area. That is the spot size that's being produced by focusing that light down to the process. It's known as the spot size. It's known as the beam waste. There are a lot of different names for it, but the end result is that it is the size of the beam that's being applied to the process. So what happens when you have variability in power density? What causes variability in power density when one of the what happens to power density when one of these parameters changes? So for instance, you have a gradual decrease in laser power. So you have some kind of component within your laser system that's degrading. It's starting to absorb laser light for some reason, and you have a gradual decrease in laser power. Well, that's going to cause you to not really understand or not really know, unless you measure it, what your laser power is doing. So you may have a spot size that is consistent at the work site, but since your laser power is decreasing, you really don't know what your power density is doing. And if you have a decrease in power, that's going to cause a decrease in power density, which ultimately is going to result in a lack of joining when you're building your part. Another example is changes to spot size or location. So you have some kind of optic within the system. We'll talk about this as one of the case examples later, but you have some kind of focus drift, which is you're focusing down to the spot, and because of a thermal effect on the laser system, your focus spot is shifting upwards. Well, what's that? And since the laser focuses down and then starts to diverge again, what's that going to do to your beam size at the work site? If your focus spot is drifting up, what's going to happen at your work site? The beam size is going to increase. So variability in your beam size when you may have a consistent power, that's going to cause you to know, that's going to cause you to just basically not understand what's happening to your overall power density. Okay, so that's what we're talking about when we talk about power density. Okay. MIT Professor Seth Lloyd, I've quoted him often in my webinars. Nothing in life is certain except death, taxes, and the second law of thermodynamics. So the second law of thermodynamics states that matter will always seek a way to revert from order to disorder because of the transfer of energy, and as a result, a system's ability to do work decreases over time. So what Seth is saying here, let me put it into layman's terms, is because a laser is made up of physical matter, it is going to decrease in efficiency over time. Because of the breakdown of the material matters, it's going to happen. Sometimes it doesn't happen very quickly. Sometimes it happens very quickly. But just because you're working with something made up of physical matter, it's going to break down over time. So because of these breakdown in the physical properties of your laser system or the components within your laser system, that's why we make the argument that it is important to measure and understand how your laser is performing, because it is going to change over time just simply because of the second law of thermodynamics. So let's talk about a laser source. Let's talk about an entire laser system, just a typical laser system in the industrial realm. So it starts off as a source. So you have this laser that you have this light being produced in some source. It's a YAG laser, fiber laser, direct diode, regardless of how the laser is being produced, and then it's sent to some kind of laser delivery system. So it's the older systems are free space optics. These days it's a process fiber, goes through shutters, apertures, purge gas in some cases, and then it's sent to some kind of laser processing head. So depending on what the laser system is being used for, this processing head can vary And these processing heads, they shape the beam, they size the beam, they focus the beam, they change the properties of the light. But the point that I want to make with respect to this second law of thermodynamics is the laser is going to be generated, and it's going to pass through stuff, and more stuff. And every single time that the laser passes through something or reflects off something, it's got the potential of changing somehow. So you might start off with this nice, beautiful, round Gaussian beam at the laser source, but because you might have a mirror misaligned, for instance, your beam may change at some point, and then ultimately when it reaches the process, it doesn't look anything like what it was generated. So this is another reason why it's not only important to measure and understand your laser and how it's performing. We make the argument that it is important to measure the entire laser system so that you know what your laser is doing at the work site. So you know not only what your power is doing, but what your spot size is doing at the work site as well. Okay, so what, I made it easy for you. I gave you your power density. I gave your power over your beam size. There are some other measurements that are very important to understand as well. So let's talk about these. Obviously, output power or energy, if it is a pulsed laser. What is your laser doing at the work site? So if you program a kilowatt, are you receiving a kilowatt at the work site? And not only are you receiving a kilowatt at the work site when you turn the laser on, but several seconds later after the laser has been turned on, are you still receiving a kilowatt? Are you still receiving what you expect to be receiving at the work site with respect to your laser power? Then there's the beam profile. Beam profile is really, just to generally define this, is what is the shape of the laser, the shape and size of the laser that's being supplied to the process. This is that bottom part of the power density equation. What's the size of the beam? What's the shape of the beam? Is the shape of the beam as it is engineered to be? Is it supposed to be a Gaussian beam? Is it supposed to be a flat top beam? So knowing what your beam shape and what your beam size is supposed to be at the work site is called the beam profile. And then there are some caustic measurements that are very important as well. So not only the location of the focus spot, which is very critical, and ensuring that the location of that focus spot is consistent and doesn't drift up because of some kind of thermal effect. There are also measurements such as M squared, beam parameter product, that are typically used in the development of the laser source, but oftentimes they're very important to measure and important to understand once the laser is put into production as well. So not only the location of the focus spot, but what the location of the focus spot is doing with respect to time. So if it's starting out here, is it staying here or is it drifting up? Understanding that property of the laser is, all these properties of your laser is very important. Again, how does that relate to power density? If you have a laser power that's decreasing, your power density is going to decrease. If you have a shift in your focus spot, your beam size is going to be increasing at the work site, which is going to cause an overall drop in power density as well. It's all about keeping that power density consistent over the build of that part, and over the duration of that laser system, so that you can protect your investment. Okay. All right. There have been many ways over the years where these parameters have been measured. There's the laser power puck. You fire the laser into this meat thermometer for 10, 30 seconds or whatever it takes, and you get a number back. It's very easy to use. It gives 1 bit of data back, but it really kind of, with your systems, it really doesn't make sense to do that. With respect to beam profiling, there's been the acrylic mode burn. You fire the laser for a couple of seconds, you get a shape. It's a good indicator of your laser, but it's also giving you just one single data point. Oftentimes it's very subjective measurement. There's burn paper. You you blast the laser for a second, you can see what the spot size is. You can kind of get a beam profile from that. Mode plates, you fire the laser at the mode plate, and you can see how the beam changes, but it's really up to the experience of the person who is taking the measurements to determine, well, is it a good laser, bad laser? There's really no industry standard measurements with respect to viewing a laser on a mode plate. These systems are all simple, they're very inexpensive, and that's typically why some people still use these, but it's not without a cost. There is a cost to using these systems. It's very subjective interpretation. One guy might see a measurement and say it's okay. The next guy might see it and say, yeah, I got something wrong. And oftentimes there's single data points. There's no trending data. And just overall, it's a very incomplete analysis when you use these legacy tools like this. Again, how is this affecting, or how are these methods really fully helping you understand what your power density is doing? Your trending analysis, is the laser power staying consistent? You just don't know. Is the spot size staying consistent? You just don't know. All right, so let's talk about some current laser measurement technologies. It's advanced a little bit. Here you see an Ophir electronic power and energy measurement. It's a fan-cooled system that's oftentimes used in additive manufacturing systems. This device here is called the Aerial. It's a wireless device. You see the readout on the system. You can also communicate with it Bluetooth, so you can communicate with it wirelessly. This is a device that gives you one single data point. I'll give you that. So you fire the laser, it gives you a data point, but it is very easy to use. It gives you very relevant data with respect to that beam on time. But I will admit that it doesn't give you a complete picture of what the laser is doing. But we're going to talk about pros and cons to that later on in the webinar. With respect to beam profiling, this is a device that we introduced. It's called the Beam Peak. It is a camera-based spot size analysis device. So it gives you your spot size, your beam shape, and it also gives you a laser power measurement as well. So with the spot size and the laser power, it can use those two measurements to give you a real-time power density measurement at the work site. So it's a really nice device. And this is a Rayleigh scatter device. It's called the BeamWatch AM. We'll talk about that in a second, but it is this will measure your spot size, but it will also measure your focus spot location real time. So if you do have any focus drift, it'll tell you how far and how quickly you have focus drift, in addition to measuring power as well. So it can tell you a graph, or it can give you a graph of power density at the work site if you do have any changes in your focus spot. These devices have industry standard analysis, so there are industry standard measurements that are being taken, ISO measurements in most cases. It gives you immediate live electronic data acquisition, so there is no guesswork as far as what you're seeing with the measurements. It tells you what you're seeing. So it just as a whole just gives you more comprehensive analysis of what is going on with your laser system. Again, how does this relate to your power density? You have a better understanding of what your power is doing over time. You have a better understanding of what your beam size is doing over time. It's just a better way of comprehensively analyzing your laser system. Okay, so instantaneous measurement versus time-based measurement. There are some pros and cons, like I mentioned a second ago. One good thing about instantaneous measurement, and by instantaneous measurement I mean the single data point. So you receive a single data point. Typically when the laser turns on, it gives you a laser power. This can change over time, as we've talked about, but these systems are very simple. They're oftentimes air cooled, so you don't need to water cool them, and they're wireless, so you put it in, you fire the laser, you get a number back. It's very quick to use. The cons is the drawbacks to using systems like this It really only tells you what the laser is doing at the beam on time. It's not really representative of true laser behavior, and sometimes, depending on the device, they're oftentimes not as accurate as some other devices. The time-based measurements, and these are the systems where you turn the laser on, you get a graph, you get a trend of what your laser is doing. It's going to give you a more true representative of what your laser is doing. These are accurate, NIST traceable, calibrated devices, and oftentimes very simple devices. The drawbacks to these are they're oftentimes fan or water cooled, especially at the kilowatt laser power level. Unfortunately, you have to plug in power to run the fan, or water lines if it's above a kilowatt or so. So they are a little bit difficult to set up in these additive manufacturing again. But again, when you're trying to understand your power density, when you're trying to understand that trend of what your power and your spot size are doing, which is better to understand, and I would make the argument that these time-based measurements are better. Then there's the conversation about in-situ monitoring. So a lot of these systems are, a lot of the process monitoring systems are on board the laser system, and like I mentioned earlier, to give you real-time feedback on what the laser system is doing, and it's oftentimes very valuable information. With respect to the measurement of the laser, there are in-situ measurements, which are called, we call it Ophir, an in-process measurement. So it's measuring the laser characteristics in process. And then there's the offline measurements, which you have to take the laser offline, so between the build of parts, but that's called the at-process measurement. So you have the in-process and the at-process measurement. Pros and cons to each one of these approaches. So the in-situ, the in-process measurement, it oftentimes can be integrated into the system. So it's really just a press of a button. The information is given to you very simply and easily, very simple to use. It gives you oftentimes continuous laser power checks, and this feedbacks to your additive manufacturing. The drawback to doing it this way, it really, in most cases, it only checks a portion of the laser system. So it will pick off the beam right before the process and analyze that beam. So it's not giving you an analysis of the overall system. The optics that are closest and most susceptible to thermal effects are really what's going to cause the problems in most cases of these systems. So, and those are characteristics that you're just not capturing with the in-situ measurements. And then also, once the system is integrated into the system, into the overall system, it's sometimes very difficult to calibrate at that point. This versus the at-process measurement, this really the main pro to this approach is it gives you a more complete measurement of the entire laser system. It gives you a more real-world representation of what your laser is doing. They can be integrated into a system. It's not done very often, but you can integrate them into an additive system to bring the laser over and to take a measurement. But again, it's not really done that often. The drawbacks to this is you have to take the measurements during the downtime. So between builds, it's going to take away from part production, but you do have to take the laser down in order to take these measurements. Sometimes, as I alluded to in the previous slide, it is sometimes it's a somewhat difficult setup for these, for these systems, but and so as a result, because they're a little bit more difficult to set up, the measurements aren't done as often as maybe they needed to be. So those are pros and cons looking at the in-process and at-process measurement. So now I'm going to hand it over to my my colleague Kevin Kirkham. He is going to talk about some case studies and where we helped some customers with their additive manufacturing projects and talk about how we helped them. So I'll hand it over to Kevin now.
Thanks, John. I appreciate what you've done up to this point. I'm going to talk about a few case studies, things that have actually been accomplished in the past. The first case study is an at process. analysis on free space optics. Looks like my advance isn't working, John. Next slide. So in this case, we're looking at an additive manufacturing system. We are using a BeamWatch type beam analysis device. BeamWatch uses Rayleigh scatter to image the beam sideways. So we're looking at an X and a Y view of the beam as it goes through focus. We could call it a dynamic caustic analyzer because it finds the beam, locates the beam waste. And in this case, we're marrying it to a water-cooled power sensor. So here's the beam analyzer on the top, the BeamWatch device, where the beam simply is transmitted through the enclosure. There's nothing in the device that interacts with the beam. It simply shines through the box and is viewed by an optical system. Again, it's looking at the X and Y distributions of the caustic. The through beam is being impinged on a thermal power sensor. So again, we have information about the we have information about the power dynamically, so we can measure power over time, and we can also measure how the beam is focusing and where the beam is focusing. So in this case, a 1-minute power check, the beam came up to power very quickly and was stable, producing the power that was requested. So the information about the intensity of the laser was good and complete. Then we monitored the beam profile. This is a screenshot of the BeamWatch software. The false color image on the right represents the X and Y images of the laser, again, as it's going through focus. So this region of the beam is called the caustic, where we're imaging both the beam before it approaches focus, the focus area, and how the beam diverges past focus. The software, because it is dynamic, is looking, it finds the initial beam location, and also the way the system is spatially calibrated, we can confer the location of the work surface relative to the how the beam is propagating. The cursor here defines where this cross-sectional intensity profile is derived from. Cursor can be moved anywhere through the beam profile, the caustic profile. In this case, the cursor is placed at the work surface. Some of the numerical analysis from the software includes the waste width, the waste location, and any changes in that location over time. So in the next slide, we can see that after a short period of time, in this case, about 10 seconds, the beam waste moved from just a little ways, about a millimeter above the work surface, to almost out of the measurement space. The total focal shift of 3.75 millimeters. So that is the difference from where the waste was first detected in the initial measurement to where the waste was detected after approximately 10 seconds. So from that information, because we know the spot size at the work surface, and we know the power density, the power at the work surface, which is represented here, we see about a 5%. I think this, in the next slide, we'll see that there's about a 5% decrease in power. Yet the power density, because of this focal shift, power density at the work surface within 10 seconds decreased almost 90%. So you can imagine how your process will be affected if the brightness of the beam at the work surface or the power density is changing by 90% over a 10-second period. If every time you turn on the laser and the power density at the work surface starts out to be appropriate, and then 10 seconds later has drifted 90% and is certainly not appropriate for the build, you can imagine how that's going to affect a long-term build. So again, with this case study, the water-cooled power sensor and it produced a dynamic and consistent measurement. The BeamWatch caustic analyzer over 10 seconds showed that the focal plane shifted over 3.7 millimeters, causing the spot size at the work plane to increase to 138 microns, which reduced the power density by 90%. So again, a 90% decrease in power density at the work surface is going to cause some issues. So what's causing this? Very typically, neglected optics. Most typically, the cover glass slide has become contaminated. In many cases, contamination that may not even be visible to the naked eye can cause thermal shift by absorbing small amounts of the power that's transmitted through that cover glass. So as some of the energy is absorbed in the optic can expand, creating thermal effects, thus changing the spot size location over time. The second case study, we're going to look again at combined power and spot size analysis and what that can tell us about the appropriateness of the laser system. This is the Ophir beam peak system. It's a little bit different than BeamWatch in that it produces a more typical beam profile as the beam is impinged directly onto a CMOS beam profile sensor. In this case, the beam path to the sensor is very well known within 50 microns. So we know exactly where the beam profile is being taken. And in this case, we can relate it to the work surface of an additive manufacturing system. So the beam peak provides a beam profile at the work surface. It has an integrated 1 kilowatt laser power sensor that's air cooled. The removable beam dump allows you to continue to work even after the system has absorbed a very large amount of energy. The system contains a defocusing lens that expands the beam that is presented to the power sensor, interfaces to a PC with a single USB cable, and includes also additional attenuation, so it can measure laser powers over a very wide range, up to 1,000 watts. Again, this device is designed to measure the focal spot, so focus spot down to 40 microns can be accurately measured with this at 1,000 watts. 19 millimeter input aperture means that it's appropriate for most additive applications. Here's a beam profile, a typical beam profile that is created or obtained by the laser beam analyzer. The input aperture is well defined, so a guide beam can be used to locate the device. Integrated thermal power sensor provides a continuous power measurement reading, which is relayed to the software. And again, it has very large capacity to absorb energy. The integrated beam analyzer, like I say, measures the spot size at the work surface and will show any changes in either the mode or the beam, the spot size, the beam widths over time. So again, with knowledge of power and the spot size, we can determine the power density at the, or fluence at the work surface. So what can happen? What can go wrong? Here we have a consistent power from this system. We can see that over time, the power is not changing. However, looking from the upper left-hand corner to the right, you can see that the beam profile changed from a very well-behaved, well-focused Gaussian beam to a somewhat distorted beam with lower energy density and a much larger spot size, and to the point where the power density has decreased significantly. Even though the power is stable, there's still the same amount of power in the laser beam. The distribution, and thus its ability to do work, the distribution of energy, thus its ability to do work is degraded significantly. So in this case, power was stable, but because of variable focusing of the beam delivery optics, we are getting significantly varying power density. Without measuring this, you simply would not know what the problem is, other than an improper build. In case study number 3, again, we're looking at combined power and beam caustic analysis. In this case, it's also an additive system. This is the Ophir BeamWatch AM analyzer. It contains a Rayleigh scatter beam profiling system at the top and a mistraceable power sensor, in this case an air-cooled thermal power sensor in the bottom of the device. So again, we're combining a beam analyzer and thermal power sensor so that we can fill in the blanks and determine the power density at the work surface. Again, this product is calibrated in the z-axis, so we know within 50 microns where the measurement plane is located. There's a calibration, the calibration information on the side of the device asks you to lower the platform that much, which places the center of the beam analysis system at the work surface. This system again uses the BeamWatch software, and similarly to the first case study, BeamWatch measures the location of the waste over time compared to the work surface. Here the dotted line represents the work surface. The blue arrow indicates where the beam waste was initially located. The green arrow indicates the current location of the beam waste. So we can measure how the power density changes over time. Absolute power is measured, as well as the power density at the cursor, in this case, the work surface. Here's the plot of the power density over time, and you can see that there's not great resolution in that chart. It does change. It does lower throughout the measurement period. So in this case, the power was changing. We noticed that over the measurement period, the power decreased approximately 13%. And because of focal shift, the spot size at the work surface also changed significantly. Total focal shift was approximately 650 microns, So that equated to a significant decrease in the brightness or fluence or power density at the work surface. So in this case, because there are changes in both the power and spot size, the power density would be completely unknown if it wasn't being measured with a system such as this. So this is all well and good. How do I avoid these pains? What are the best system practices for your AM laser? What is the care and feeding, and how do you maintain your system? The key, I think the initial key is understand how the system is supposed to be performing. And the best way to do this is to measure it. If you don't have a beam profiling system of some sort, make sure at least that you're measuring power, because small changes in power can indicate degradation in the beam delivery optics and may also indicate other issues within the laser system. So any measurements are better than no measurements. Verify how it's behaving. If you can measure the dynamic characteristics, meaning power over time, or power, better yet, power density at the work surface over time, then you'll be alerted to any potential issues before you have a build that fails or you start creating scrap. Properly maintain your system, become familiar, ask to be trained on how to clean the protective glass, make sure that the cooling water for the laser, that filters and optics are changed according to schedule. Of course, if you can measure how the laser is performing, you may be able to decrease some of the preventative maintenance scheduling by knowing that especially with optics and cleaning, that things are stable. So cultivate a relationship with your systems provider. I'm sure you'll have an opportunity to know the systems provider, service people, ask questions, and again, ask for maintenance training when your warranty period or your service account expires. You know, become the expert. There's no reason not to become familiar with how your system operates, and so you can maintain it more readily.
All right, just kind of wrapping things up here. There's a couple of quotes that I usually like to reference in my webinars, and they're very similar quotes from two very different people. Picture here is Lord Kelvin. He lived in the 1800s. He was a scientist. And speaking of physical science, he says, if you can't measure it, you can't improve it. Okay. Peter Drucker, you may recognize his face. He was an entrepreneur that lived in the mid 1950s. Speaking of workplace efficiency, he said, if you can't measure it, you can't manage it. And I like using these quotes because they're saying the same thing. Two different men lived at two different times, talking about two very different things, effectively saying the same thing, that if you have a process or if you have a system and you want to improve it or if you want to manage it, you have to measure it. You have to be able to measure it, take those measurements, analyze them, and know how to use the analysis of those measurements in order to improve and manage your system. So that's all that we have to present. Brad, I know we have just a little bit of time for a Q&A at the end, but we can entertain any questions right now if you'd like.
Excellent, great presentation. Thanks to both of you. Really good, useful information. I'm sure our attendees will be able to use. We do have some time left over for questions, as John said, and we do have some questions coming in from the audience. The first one is, are at process measurements done on the primary axis of the machine? So does this mean that you measure the same location in the optics, or can you make measurements off axis, such as the corners?
That is a question that we get asked quite a bit, and the answer is, with our laser measurement products with respect to laser power, you can measure off axis. You can measure on the primary axis, you can measure off axis, but that's probably not what the asker of the question is asking. They're probably interested in consistency between the perpendicular axis and at the four corners or at the edges of the build, and that's a fair question. That is something that we are addressing, but I'll admit to you, I don't know that we really have a solution that does that right now. Kevin, do you have anything to add to that?
It depends on the device. The BeamWatch AM designed for measuring the caustic AM systems, AM lasers, can accommodate ±5 degrees off axis. But that does not mean you can measure the beams in the extreme corners. The device will not fit to access the extreme corners in many locations. However, it will measure multiple systems with multiple beams. Some of the systems have 4 beams, some of them have more than 4. And to my knowledge, our systems can accommodate all of the lasers in a system, primarily where the beam is normal to the work surface.
Good. Okay. Thank you. Next question is, what happens when power density falls out of its desired tolerance?
Yeah. So if you can imagine what similar to what Kevin said about the fluence of the laser, the intensity of the laser light, each material has got some kind of power density range that has to be kept in order to achieve a desired result. So regardless of what you're using the laser for, if you want to weld, you want to cut, you want to join, you want to ablate, you want to heat, regardless of what you're using the laser for, there's a desire, there is a power density band that needs to be kept in order for that desired result to happen. When it falls outside of that band, and typically what will happen 95+% of the time is that the power density is going to decrease. Well, if you have power density that is decreasing and falling outside of that band, what you're going to get is a lack of joining in an additive build, for instance. And so we make the argument that knowing what your power density is and maintaining its consistency over long periods of time is going to help you ensure that those builds are going to, those layers between the builds are going to be consistent. I mean, it makes sense that if you have a consistent laser power and a consistent focus spot size and location over time, then you're going to turn the laser on. It's going to be performing consistently over long periods of time, and that's how we, ensure that, or help ensure that laser consistent.
Good.
You can imagine some of the porosity that could occur in a build if the power density decreases by 90%. I mean, that would be catastrophic to the build.
Sure. Okay. So if the laser power never changes, but focal shift does. So what's the concern there then? Your power is not changing, but focal shift is changing.
The concern, one concern that I have with that scenario is that there are still a lot of people who are maintaining lasers who think, I'll just take a power check, or they'll advise to their customers, all you need to do is check the power. Well, like we discussed in this webinar, that's a good indicator of how your laser is performing over time, but it's a very incomplete picture of how your laser is actually performing, because your laser could stay consistent, your laser power could stay consistent, even if you turn the laser power on and it's rock solid for several minutes. That's not going to tell you if your focus spot location is changing. So you could have a consistent laser power, but if you have some focal drift, your beam at your process is going to be increasing, and that's going to be decreasing your power density. So that's really the main concern.
Okay.
With that particular change in that particular mindset.
Okay. All right, good. Any other questions from the audience? We've got maybe time for one more. Otherwise, we're getting kudos from our attendees. So nice job, John and Kevin. Yep. So, yep, thank you for an outstanding and informative presentation. And thank you to our audience for attending. We hope you found it to be valuable. By the feedback, it seems like you did. So, and again, as we said at the beginning, please remember that an archive of the program will be available to you through our website. And so you'll receive an email from us within the next day or two when the event is available for you to review online and share it with others in your organization. So again, thanks to John and Kevin, thanks to our attendees. You can close your browsers now, and we wish everybody a great afternoon.
Thank you very much, everybody.
Thanks. See you.
Take care. Bye-bye.